Uranium is closely related to nuclear energy storage. This is the main use of natural uranium these days. Even though nuclear energy is obviously not in organic chemistry, I'm going to give you a quick, very concise and primitive overview of nuclear energy picture and problems in this area. So what we are talking about? When one neutron strikes uranium isotope 235, keep in mind 235 is not the main isotope of uranium. Most of uranium is 238. So we are talking about 235 only. What we'll have one neutron more, so we'll have unstable uranium-236 that in turn splits apart into two nuclei of slightly different mass. For example, strontium-90 and xenon-143, two very common daughter. And as a result, we have three additional neutrons that can go further and continue this reaction. Reaction can be written in such form: uranium-235 plus 1 neutron, strontium-90, xenon-143 plus 3 neutrons plus energy, and this is most important part. Now, energy comes from the difference of masses of our starting products minus what we have at the end, multiplied by c squared, mc squared equation. This energy will be equal around 10 power 13 joules per mole of uranium-235. Just a reminder, 1 ton of coal will give us 10 power 10 joules. So 1 mole of uranium-235 will give us 1 million times more energy than 1 ton of coal. This is a different value. This is a different scale from energies coming from chemical sources. 1 million times more. Now, what we name nuclear chain reaction is self-sustaining sequence of nuclear fission reactions. The minimum mass of fissionable material required to generate self-sustaining chain reaction is so critical mass. One more concept, we'll look at it in a moment. So what happens? We have uranium-235 taking 1 neutron, splitting into strontium and xenon, making 3 neutrons. These 3 neutrons will strike 1 more uranium, and some of them will go into nowhere, will be absorbed, will go out of reaction area or something, and just slow down. Neutron is a particle, it can slow down. So this uranium will split into antimony and niobium. This will split into barium and krypton. But again, they'll be making 3 more neutrons, and the reaction will continue. There is one concept of effective neutron multiplication factor, K. Now, we know that we have 3 neutrons, but destiny of these neutrons is different. K is average number of neutrons from one fission that cause another fission. The remaining neutrons total was 3, either are absorbed in non-fission reactions or leave the system without being absorbed. The value of K determines how nuclear chain reaction proceeds. If K is smaller than 1 subcriticality, system cannot sustain a chain reaction, and any beginning of a chain reaction dies over time. For every fission that is induced in system, average total of 1 over 1 minus K fissions occur, and game over, it stops. If K is exactly equal to 1, we have criticality. Every fission causes an average 1 more fission, leading to fission power level that is constant. Rate of reaction is the same, and reaction can continue infinitely. Nuclear power plants operate with K equals 1 unless power level is being increased or decreased. If K is larger than 1, you have supercriticality. For every fission in the material, it is likely that there will be K fissions after the next generation time, usually noted as Greek lambda. The result is that number of fission reactions increases exponentially. Nuclear weapons are designed to operate under this state. Now, chain reactions are very similar in many different areas of science. The same are chain reactions in synthetic chemistry. For example, ethylene polymerization is chain reaction. The same is contagion, how infection diseases are spread among population, among animals, among bacteria, or humans. So, in this case, if K equal 2, each person infects 2 more people, and we showed transmission this. Well, we do not say K. Biologists and epidemiologists are different people than nuclear scientists, so they say R factor. So, for example, in some contagious disease like measles, contagion factor can be 5 for fully susceptible population. And this is how vaccination works. If you remove 4 out of 5, you will not have exponential growth. If you remove slightly more than 4 randomly, the epidemics will die out. So now back to nuclear chemistry. When neutron strikes uranium-235, it splits into 2 different isotopes, and relative amounts of different products depends on mass number in such a fashion. You have minimum at 120, one isotope is around 100, and other is at around 140. So you have plenty of different products, and all of them, of course, are radioactive. How the reactor is designed? The active element is not pure uranium, but uranium oxide, U3O8, mixed valence. And this is never uranium-235 pure, because purification to isotope 235 is very expensive procedure. You can even run on natural amount, but usually we increase amount of uranium-235 2 or 3-fold. So Uranium fuel is immersed in a vessel, so neutrons can be go. And there are additional control rods that can absorb neutrons. And thus, we can control the reactor. You can see refueling process. Of course, nothing can be done manually. It should be sophisticated machinery that works in this highly dangerous area. This is how this rod works. Small pellets of uranium oxide are put in zirconium cast, so the rod is made mainly of zirconium. It's important to remove hafnium for zirconium because hafnium absorbs neutron, stopping the reaction. So the whole assembly with multiple rods look like this is fuel assembly, and it can be put back and forth into reactor. The whole reactor building contains reactor itself, core with nuclear fuel. There is a pump and control rods, so there are several systems that moderates. Rods are made mainly of cadmium. There is also graphite moderator, and often that's boric acid used as a solution. There is a control instrumentation room far away from reactor, and overheated steam coming from heat exchanger is coming to electric generator. Now the problem is that controlling and running reaction at K exactly equal 1 is very difficult task. What happens that addition of that or other isotope of fission products changes parameters of reaction. So the system needs to be continuously controlled and its behavior corrected. If controlling is going wrong, so if reaction is going wrong, you have an explosion. Explosion is not a nuclear explosion. What happens that when reaction is going exponentially up, you have overheating of your water. It boils almost instantaneously, and you have 1,000-fold expansion of reactor interior that throws away whatever is inside. Also at very high temperature, we are talking about 1,000 degrees, zirconium starts reacting with water, making hydrogen, and hydrogen reacting with oxygen can create one more explosive mixture. So lots of dangerous and unpleasant. This is Chernobyl Reactor 4. That is, as far as we have now, the largest accident in nuclear energy. Second largest is Fukushima in Japan. The problem is not explosion itself. The problem is radioactive isotopes that are coming into environment. Some of them are short-living, like iodine-131, that decays in several days. Others are longer-living, like barium-zirconium isotopes that survive around 100 days and then decay. After several years, the main contamination is coming from cesium-137 isotope that becomes dominant after 4 years or something. It's cesium contamination map around the plant. You can see the scale, it's 100 miles. So within more than 100 miles, there are areas of severe contamination. And these spots are visibly random, depends on meteorology where it fell down. So it's a little fun and very dangerous. That's why nuclear energy, despite its obvious efficiency, it's still too much dangerous to run in highly populated areas.